Hello everyone, myself Ketan Bhavsar, Assistant Professor in LJ Engineering College, Ahmedabad. In VLSI design subject, right now we are in unit number 3, MOS transistor, and today's topic we discuss about the channel length modulation. That what exactly the channel length modulation work and how channel length modulation will affect a specific MOSFET when we increase the voltage of VDS. In previous session we discussed about MOSFET current and voltage characteristics, and also we discussed about how MOSFET transistor is actually working when we provide a sufficient amount of voltages in terms of a linear region, saturation region and cutoff region. And also we prove the drain current ID equation for the linear and saturation region. And specifically for the linear region we have a value of ID or specific drain current equation. ID is equal to mu n Cux by 2 W by L into 2 into VGS minus VTO into VDS minus V square ds. And when we're talking about in saturation region, then we directly take mu n Cux by 2 W by L VGS minus VTO whole square. So we already proved these two equation, and those two equation is very popular in each and every mathematical terms or each and every CMOS level calculation when we study any types of data sheet of any sensor or any motors or any specific gadgets, electronics. So it is very useful when we are dealing with this type of MOSFET. Now, as per today's topic, we move on channel length modulation. So what is channel length modulation? First of all, the question arises in our mind. The effective channel length between the drain and source is reduced in saturation region. So as you already know, we have a three region, linear, saturation and cutoff region. In saturation region, as we know, if VDS is increased more and more, if VDS is greater than or equal to VGS minus VTO, then the channel length is start reducing, as you already know, and after some time it create a pinch off point that we already seen in previous session. So the drain current equation for reduce the channel length is called a channel length modulation. So when channel is start reducing, fine, so we have to calculate the drain current for particular that situation, and it's called a channel length modulation. Now as you can see, this situation is similarly to the pinch off point, or it is a pinch off point situation. As you can see, the channel is established the first year, and if you increasing VDS more and more near the drain terminal. So after some time, what exactly see that these are the scenario is established when we talking about the channel length modulation. And also make sure that we assume VB is equal to 0, means substrate bias effect is equal to 0 in this particular situation. So the pinch off point, so we have already this equation we already proven in pinch off point or near the pinch off point in previous session, that Q1 of y is represent the channel from y is equal to 0 to y is equal to L, minus COX VGS minus VTO minus VC of y. VGS minus VTO is represent the drain current to source current equation, which is VDS is greater than equal to VGS minus VTO, and VC of y is represent the channel voltage from y is equal to 0 to y is equal to L. So in inversion layer, it's y is equal to 0. We assume that VC of y is equal to 0. So Q1 of y is equal to 0 minus COX into VGS minus VTO, because VC of y is approximately 0. So in channel length modulation, the inversion layer change from y is equal to L to y is equal to L dash, because of the pinch off point, your channel is displacement from y is equal to L to y is equal to L dash. So displacement factor is equal to delta L. So now your channel inversion, in inversion layer channel length should be y is equal to 0 to y is equal to L dash. So VC of y is equal to VDS is equal to VGS minus VTO. So Q1 of y is equal to L dash is equal to minus Ux into Vgs minus Vto minus Vc of y, because in this particular situation we assume that y is equal to L dash we have, because Vc of y, so y can be L dash right now. Fine. In previous session we assume y is equal to 0, so we take q1 of y is equal to 0 is equal to minus Ux into Vgs minus Vto. So here you assume that it q1 of y is equal to L dash minus Cux into Vgs minus Vto. We already seen the Vc of y at particular pinch of point or L dash Vgs minus Vto. So because of this situation, all the Vgs and Vto will be cancelled out. So finally you get q1 of y is equal to L dash approximately 0. Because this situation is established only when Vc of y is equal to Vgs minus Vto. Fine, the channel will be in saturation region when Vds is greater than or equal to Vgs minus Vto. So what exactly Vc of y? So Vc of y at y is equal to L dash, we have Vgs minus Vto. So approximately we are getting q1 of y is equal to 0 in this particular region. So because of that region, channel will not form. So the total channel length modulation L is equal to L dash plus delta L that we had seen, because you have a total channel length y is equal to 0 to y is equal to L. So your total channel length L and the combination L dash plus delta L, because L dash is represent a specific new pinch of point, a particular channel point, and delta L is represent the displacement vector. So if we increase a Vds is greater than or equal to Vgs minus Vto, so as you can see, now your total channel length, it started from y is equal to 0 to y is equal to L. So now it becomes y is equal to L, instead of L it became L dash. So in channel length modulation, we have a same equation for the drain current ID in terms of the saturation region, but instead of L we have to write down L dash. This one is the only change when you write down a ID equation for saturation in channel length modulation. So ID saturation is equal to mu n Cux by 2 W by L dash into Vgs minus Vto. So as you already know, the Vds is equal to pinch of point, so Vgs minus Vto. So L dash is equal to L minus delta L, that you already know the effective channel length because of a channel displacement vector. So now we can write down, instead of L dash, ID saturation is equal to mu n Cux by 2 W by L minus delta L instead of L dash, because L dash is equal to L minus delta L. So Vgs minus Vto whole square. So we can also simplify this equation from ID saturation is equal to mu n Cux by 2 W by L 1 divided by 1 minus delta L by L. So Vgs minus Vto whole square. So we simply divided by delta L in this particular situation. So we just simplify 1 divided by 1 delta L by L mu n Cux by 2 W by L into Vgs minus Vto whole square. So when Vds is more than Vgs minus Vto, so we directly write down 1 minus delta L by L is equal to 1 minus lambda Vds. It's basically a lambda like a channel length coefficient. We also prove the gamma coefficients for specific threshold voltages, and here we also prove a lambda for a channel length modulation coefficient. So lambda Vds is less than 1. So ID saturation is equal to 1 divided by 1 minus lambda Vds into mu n Cux by 2 W by L Vgs minus Vto whole square. So in this particular region, we can directly simplify this particular equation using this term. So ID saturation is equal to 1 divided by 1 minus lambda Vds into mu n Cux by 2 W by L Vgs minus Vto whole square. So in exam, if someone asks you that write down the lambda equation, that you have to also write the channel length modulation equation, explain the pinch off point in detail with mathematical terms, then you also have to prove a channel length modulation. Similarly, if you also have to prove a channel length modulation equation delta L or L dash, then you have to write down the equation for ID saturation 1 divided by 1 minus lambda VDS into mu n Cx by 2 W by L VGS minus VTO whole square. So we have equation is look like this. Finally, ID saturation is equal to mu n Cx by 2 W by L VGS minus VTO whole square into 1 plus lambda VDS. So due to the channel length modulation, the saturation current increased slightly. So now your graph is look like this, that it will increase slightly as compared to a linear and saturation region that we already seen in current and voltage characteristic in previous session. So now with help of this graph we can easily see that as per the VTO, it's a threshold limit over. This one is a drain current and drain voltage VDS. It will be slightly increases gradually if the lambda does not equal to 0. So now I hope that you are getting idea about what exactly the channel length modulation is and how it will work. So now I hope that you really like this session and you definitely get the idea about channel length modulation. It is very simple, like you have to take a channel from y is equal to 0 to y is equal to L, and now because of the pinch off point the L became now L dash, the displacement vector delta L. So L is equal to L dash plus delta L. You have to write down the same equation for the ID saturation. Instead of the L you have to put L dash, and now you have to put L dash is equal to L minus delta L and divided by L and prove the lambda base equation. So it is very simple if you already know the current and voltage characteristics for a MOSFET, and then you directly know what exactly channel length modulation is or lambda coefficient is. So now in next session we're talking about the MOSFET scaling, like how you scale a current and voltage, and based on the scaling factor how we increase or decrease the voltage value. Drain current and voltage characteristic is actually work, and what exactly you can see the change between the current and voltage characteristics in terms of the MOSFET and channel length modulation. As you can see in saturation region, it will slightly greater than a specific linear and saturation region because of the channel pinch off point, and also displacement vector. Here you can see the lambda coefficient which represents the gradual channel representation and channel length modulation. So basically in this particular area you can see the linear region, and here you can see the saturation and pinch off point. So this point is play a major role when we discuss about a channel length modulation, and also it play a main role when we discuss about what exactly the displacement vector will be generated for a specific channel length, and it should be a delta L. So I hope you getting the idea about what exactly the channel length modulation is and how it will work. In next session we discuss about scaling, what exactly the MOSFET scaling is, and we discuss about also a current and voltage characteristic in terms of the current, what exactly the role of current when we discuss about the real-time applications, and also the importance of voltage scaling. In terms of the voltage scaling, it also play a main role when we discuss about a specific current, specific area, specific width, specific dimension of specific MOSFET area. So it play a main role when we discuss about the scaling factor, because what exactly the meaning of scaling? Scaling is all about the measurement, and it's all about a specific limit that you have to set with a measuring current and voltage characteristics for specific component. So we discuss about a scaling factor in detail in next session. So I hope that you are getting idea about channel length modulation and what exactly the MOSFET scaling is, and how it play a main role when we discuss about a specific characteristic of MOSFET. So I hope that you are getting about the channel length modulation. So